Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently based at the University of Helsinki in the Helsinki Institute of Physics. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, basically all of the cool things happening inside the universe. I mean, I don't study everything in the universe, that would be way too much. I do focus on topics. Hey to David, nice to see you both, David Dunn, David Howden, great to see you here in the comments. Thank you for joining, as always, great to have you here. So yeah, I study the universe and fun stuff happening inside the universe. And I love chatting about science. Hey, Paul, great to see you, as always. Really nice to see the regulars coming in every single week without fail. I love your dedication to the show, all of you. Like, you're always here, the regulars. Great to see you. Great to have you here. So, yeah, I love talking about science. I love talking about cosmology, about what it means to be a scientist. And I like jumping here on YouTube, on Twitter, wherever you're watching me from, and chatting about all of the cool things that I get to study and about what it means to be a scientist and, you know, just in general, chatting and answering people's questions. Some weeks I prepare topics, some weeks I have guests. This week I have neither. I'm just going to wing it like the old days in Periscope and see what happens. So if you have any questions about the universe, any questions about cosmology, any questions about academia, anything you want to discuss, feel free to ask away and I will try to answer your questions. Hey Keith, great to see you. Thank you for joining. The one on entanglement that I posted last week actually wasn't a live episode, so we recorded the entanglement one some months ago and streamed it on HAPS, and I just uploaded it to YouTube over the weekend, last weekend, because I couldn't do a live stream. So I uploaded one of the old ones. I have a few like that, actually. I have a bunch of live streams saved from the HAPS days that I'm gradually going to upload to YouTube on days when I can't do a stream. So then any Sunday when I can't do a stream, there will still be an episode. I've decided that's how I'm going to gradually upload the old ones. Hey, James, great to see you as well. Another one of the regulars. Great to have you in here. So, yeah, I'm here to answer any questions people have. Just to give you a bit of focus, and before I start on that, as always, if you haven't subscribed to the YouTube channel, please do so. Please like this video, leave a comment down below. This all helps with my engagement. It helps build up the audience, and I appreciate each and every one of you who engages with the streams in any way. If you're watching over on Twitter, thank you. I appreciate you watching on Twitter as well. If you want to join the conversation, you want to head over to the YouTube channel. I'm easy to find on YouTube. And if you go to the tweet directly beneath whichever one you're watching on, like on my profile, the tweet directly beneath, there's a link to the YouTube stream as well. So if you want to ask questions, do head over to the YouTube stream because that's where you can join in. But if you just want to sit and lurk in the background and stay on Twitter, that's perfectly fine as well. Counts of views in different places, but that's perfectly fine. And as Dave Dunn is saying, like, subscribe, click the notification bell. I think that's what people say as well, you know, all of the YouTube stuff. And we already have a question coming in from Paul. And before I get to that, just a reminder of the type of topics that I like discussing. I mean, I like pretty much everything in the universe. I'm not exclusionary to my physics topics. I don't think there are boring things in the universe. Like, everything in the universe is fun to study and fascinating and cool. And I don't think there are boring research topics. So, yeah, the things that I like the most are obviously the cosmic microwave background radiation, the CMB, the oldest light in the universe. That is the background radiation that we can see behind everything else, and it gives us a picture of what the baby universe looked like. And of course, we are not going to have a CMB conversation without this image coming up on screen. It took me less than 5 minutes today to find a reason to flash the CMB image. That's potentially a new record. So yeah, cosmic microwave background radiation, always happy to answer questions about that. I see Paul's question already contains the CMB magic word, so that's nice. I've also worked a lot on dark matter, trying to identify dark matter. So dark matter is this mysterious type of matter that's in the universe that accounts for 25% of the energy budget of the universe. It interacts by the gravitational force, but it does not interact by the electromagnetic force, which means it is basically invisible. I spent a lot of my career, I say like it's a long career, my whole life. I spent a lot of my research time from my PhD to my first postdoc to now working on dark matter models and how we can ask the universe to help us constrain dark matter models. And recently I shifted into gravitational waves, which is an incredible topic because I get to study these tiny, tiny ripples in the fabric of space-time that can tell us a huge amount of information. And the gravitational waves that I focus on tell us about the first few seconds, the first fraction of a second of the universe. And it's incredible that I get to study that. And it's really incredible to think also if we can use these primordial gravitational waves to constrain dark matter. And I just realized I am slightly hyper and speaking way too quickly. So it's because I started with the CMB. So deep breath, everyone, or deep breath myself. And let's get into this slightly more calmly. And I see there's already a few questions to answer. So deep breath, and then we can jump into questions. And I stop rambling. Okay, that is not bringing down my energy levels. Today is going to be hyper. Hey, Scott, thanks for popping in to say hi. It's always great to see you. And I know you can't stay today, but I appreciate you coming in just to say hi anyway. Okay, so let's go back to Paul's question. Does all the plasma in the heliosphere distort the frequencies or other aspects of the CMB to make it hard to be accurate in that direction? You know, this is a really, really, really cool question. And this is one of the reasons. So anytime we're looking at the CMB, there are several different probes we can use, or ways we can go about measuring the CMB. We can use ground-based observations, such as the ones being done by the South Pole Telescope or the Atacama Desert Telescope. These are ones that are ground-based. And what these ones do is they focus on a chunk of the night sky. And here, of course, they will point away from the sun. That's why we do the sky, like the night sky. You point away from the sun. You don't get the photons coming from the sun to mess up your system. And then you only focus on a small chunk of the sky, but you can get really, really good resolution on that small chunk that you focus on. Or small, you know, sometimes like a whole fraction of the sky, but always away from the sun. On the other hand, there's ones that we can send to space, such as what we did with the COBE satellite, the WMAP satellite, and the Planck satellite, which is the one responsible for giving us this image here. This is our latest Planck measurement of the CMB. And what we do with these type of missions is we send them to what is known as the second Lagrange point. So there are 5 Lagrange points in any system of 2 bodies. So if you consider the system of the Sun and the Earth, there are 5 Lagrange points in this system. And Lagrange points are places where it's easy to keep satellites because the gravitational forces that the satellite feels coming from different bodies keep it in equilibrium. So it feels enough gravitational pull from a few things combined with its own motion that it's kept basically in orbit. It's an ideal place to dump a satellite where you then don't need to worry about spending too much fuel to use it. And there are different Lagrange points placed in different positions. So there are 2 that are somewhere in between, trying to think by memory where they are. If you consider Sun and Earth, there are kind of 2 that are up here. So in between the 2, there is one right in the middle. So Earth is here, Sun is over here. Let's say my head is the Sun, this is Earth, because then I have 3 things. So you can have one Lagrange point kind of up here-ish, one kind of down here, you have one in the middle, you have one this side of the Sun, and then you have what is known as Lagrange point 2, which is over here. And it is the opposite side of Earth from where the Sun is. So if you consider Sun, Earth, Lagrange point 2 is behind it. Now, anything at Lagrange point 2 is going to be in the shadow of the Earth. And this is extremely useful because on the one hand, it lets you cool down your satellites a lot, which a lot of these satellites need to be really, really cool for their mechanisms to work properly, such as the just wonderful space telescope, JWST, that is at Lagrange 2, and Earth's shadow keeps it very, very cool. The other advantage of being at L2 is the Earth blocks the Sun from you. So then when you are L2, you don't directly get the light coming from the Sun. At this point, you can do an all-sky survey. You are going to have some things that are going to cloud your vision slightly, especially if you're looking at CMB photons. You're going to have like the whole Milky Way in the middle of your satellite, in the middle of your image. So you end up with basically the Milky Way in the middle because that's how you're looking around, and then everything else. But the Sun at this point is basically behind the Earth from where you're looking, which means you don't get the big bright source that is the Sun. So back to your question specifically, because that was a bit of a ramble to get to the point here. Does all the plasma in the heliosphere distort the frequencies or other aspects of the CMB? It doesn't, because the CMB missions will look basically, the satellites we send for CMB missions will look everywhere except at the sun because the Earth blocks them. And now if you consider, once it's there, the Earth is just going to be very, very small points on the CMB, so not enough to register. The sun is not going to be distorting you because it's far away and behind the object, behind the Earth. So we basically get away with that by kind of hiding the sun. So it's a great question because you'd expect that all of the photons coming from the sun would be a huge source that could affect how you measure these photons, particles of light coming from the background radiation. But we're at L2, so we don't need to worry about the sun. As for the Milky Way, when we look at the image of the CMB, now this here is a heavily processed version. What the real images look like is in the middle, you actually have a band where you have the Milky Way. And there, everything is kind of red because it's just like really high energy photons coming from the Milky Way itself. However, we know how to mask this. There are techniques you can use where you take kind of this chunk of the sky and you can get rid of it. You can use different methods to actually get rid of the clouding that you have from the Milky Way, and also going to different frequencies helps. But if you look at more raw images of the CMB, not just like heavily processed one, you do see a band in the middle, which is the Milky Way. Now, the good thing is we're always doing 2-point statistics here. So we're not so much interested in if this individual patch here is blue and this individual patch here is red. What we are interested in is the overall statistical properties. So then if we have a bit that we know is clouded by the Milky Way, it doesn't matter so much because we don't care if that specific photon that is behind the Milky Way is hotter or colder because we have the overall statistical properties. It is very similar to using Photoshop to cut out an X of a photo, but you don't want to cut them out completely because then you'd have a gap in your data. You kind of want to remove it without removing all of the information. Right? It's like if the person you're cutting out with your photo is standing in front of a pretty mountain, you want to remove the person but leave the mountain behind them. Just like remove this person but fill in the background. That's kind of what we do to get rid of the Milky Way band. So we don't need to worry so much about, yes, the Earth only partially blocks the sun at the L2 point. Thank you, David. That is correct. There is still going to be some light coming from the sun, mainly because sun's a lot bigger than Earth distances, but it's not to the point that it will cloud your measurements. At that point, you're not close enough to need to worry about the heliosphere directly, and you're at a point where the photons that you would get from the sun are going to be points that you can easily remove from your map. So you don't block it completely, but you block it enough for it to not be a problem. So CMB measurements, in general, you don't need to worry about the sun. If you're doing a ground-based measurement, you just point your telescope away from the sun. If you're doing a satellite mission, you go to L2, you use the fact that you're partially blocking the sunlight, and then it becomes easier to get rid of that information. But that is an excellent question, and it's a very, very good thing to think about, of basically going to the question of how do we do these measurements. There is another cool effect in the CMB, which is also something we know how to subtract, which is the motion of our galaxy. So we know that we are rotating within the Milky Way. This produces a motion, a preferred direction. So when we look at the CMB, the background photons, there are going to be parts that will be blue shifted and parts that will be red shifted due to the Milky Way spinning. This Milky Way is rotating, so we're going to see some areas of the night sky that are moving towards us and some that are moving away from us. This is just because of the motion of the Milky Way. So again, if you look at the slightly unprocessed versions of the CMB, you actually have a nice dipole that you can see on it of like this part here is blue shifted, this part here is red shifted. But because we know approximately how fast, we're moving within the Milky Way, we know how fast our planet and our solar system is spinning around the Milky Way, you can subtract that velocity and then you get the CMB map that I always show you. So there's actually multiple steps involved. Like producing this map here is a huge amount of effort, and it goes through several cleaning steps where we remove the dipole, we remove the astrophysical sources, things like galaxies, we remove the Milky Way. So getting to the point where we have this image, a lot of cleaning and processing has been done to get to this point. The good thing is this is done by multiple different teams. There's a lot of different methods and everyone kind of agrees with the end result. So even though it's a processed image, it is considered very trustworthy image. We know all the steps that go into cleaning this. So this is obviously the version I always show people, but there are plenty of kind of in-between versions of the CMB, from here's the actual raw data to here's the clean, final, pretty data. But yeah, there is a lot of stuff that we need to be aware of when doing this measurement. So I think that's an excellent question, Paul. And on that note, now I'm going to leave that for later. Just a slight hint of something I want to happen someday on the show, but I'll leave that for just later. Just leaving you on that note, hints, and then cutting it off. Like, teaser, not even. Okay, let's move on to the next question. How often is the CMB updated? I know that's not the next question, but on the topic of the CMB, I know there were other questions about gravity, so I will go back to those. But how often is the CMB updated? Now, that is an interesting question here, James. Do you mean how often do we get a new map, or how often does the CMB change? Because both are very interesting questions. Now, if your question is how often does the CMB change, well, these photons from the CMB are constantly being redshifted. Today, we observe them in the microwave range of the electromagnetic spectrum. But if you went back to just at the time when the CMB was produced, these would be much, much, much higher energies, because they haven't had time to be redshifted. They haven't stretched throughout the history of the universe, and they haven't expanded. So if you go back to very early times, you would be at much, much higher energies. So there was a time in the history of the universe where the entire night sky would have been aglow with the CMB, like visible photons. They would have been in the visible frequency range. Now, at this time, the Earth wasn't around, the sun wasn't around. We're talking billions and billions of years ago because of the way photons redshift. But there was a time where the photons of the CMB would have been illuminating everything in the universe, because they would have been in the visible range of the electromagnetic spectrum. Now they're in the microwave range, and they are gradually going to be redshifted and redshifted and redshifted. And then you also have the thing that the CMB photons get kicked about a bit by going in galaxies, by the expansion of the universe, by different things happening. So it's always fun to ask the question of how long would we have to wait to see an entirely different CMB map? And this is actually a question that I got asked once on a stream years ago, discussed it with colleagues, and then somehow we happened to set this exam on the next advanced cosmology course. This was a question we set on the exam. So how long would we have to wait to see a completely different CMB map? The answer is 10,000 years. So if you look at the CMB again in 10,000 years, you will see a very different map. Now, if your question was actually how frequently do we get a new map from data, well, the first map that we had was produced by the Kobe satellite in 1995. This was the first satellite that we sent up that produced this spectacular map. Then we had Boomerang in the early 2000s. Then in 2001, we launched WMAP. WMAP took data for 8 years. Hey, Jans, great to see you. No worries, you just missed me talking about the CMB, and I'm sure you've heard that many times before, and we are still on the topic of CMB. So we had WMAP in 2001. This took data for 9 years. I think there were 3 data releases with WMAP. So it took data for 9 years, and there's the whole cleaning, the processing, and releasing everything. So then you get WMAP release 1, WMAP release year 3, and WMAP release year 9, if I remember correctly. Then we had Planck. Now, Planck was launched in 2009. It took data between 2009 and 2013. So you took quite a lot of data. And then it takes a very long time to process this data, to clean this data. As I was saying before, we have to remove the Milky Way, we have to remove the dipole, we have to get rid of all of the galaxies, we have to clean it, we have to get rid of the noise the satellite is making itself. So processing the data takes a lot of time. So this map that we got from Planck, we got one in 2013. We got a second Planck map in 2015, even though data stopped being taken in 2013. And the last map we got from Planck, the most accurate map we have of the CMB, is this one from 2018. So it took 5 years between the mission ending and this final data to be released, but that is the last one we have. Now, this is the last one we have from a satellite. There are ground-based missions pushing this even further. We already have data from the Atacama South Pole Telescope, from the Atacama Telescope and from the South Pole Telescope. Both of these are ground-based. As I mentioned before, the ground-based ones only focus on a chunk of the sky and not the whole night sky, because they're ground-based, so they can't look everywhere. But the chunk that they're focusing on, they can really focus on. So there are individual parts of this CMB map where you could put new versions on top, like here's a SPT one and here's the ACT one. So you can update it, but a complete sky map of the CMB, the last one we have so far is from 2018, and currently there are not missions planned to take this again, because we already have incredible precision here. Now, what we are going to do is do the same map with polarization, with lensing, and with other things, and maybe someday with spectral distortions. But in terms of the temperature differences, this is basically currently the final word, the final say we're going to have. So that was a long answer to the question, and I hope that answers your question. If I have for a 4 TB external hard drive, can I fit the raw data? If you mean all of the raw data from Planck, no, absolutely not. We download, so anytime I use the Planck data, I download what we call the like reduced data, which has been cleaned and processed a bit and is not the raw data. And this one is about 2 gigabytes. It's not so big, 2-3 gigabytes. But this is after things have been done. But the raw data from Planck, I don't know how big it is actually, but I think it's a lot bigger. I would have to look that up. I don't have a figure to give you off the top of my head. Okay, I'm going to give a few seconds to see if more CMB questions come in, because as you know, I can't just walk away from the CMB easily. And then I'll go to the other really cool questions about gravity, about wave functions. So just giving you a few minutes to throw out a CMB question. And given that there's a lag on YouTube, I won't see them because now I'm already going to go back to the other questions. Back up, back up. Okay, it's good that I have infinite scrolls here on Restream. It makes it so much easier to find your comments. Let's see what the next question was. Try not to kill myself on my tea in the meantime. So there was a comment here by Keith of random matrix theory and black holes. I'm not sure if that's a question or a topic request. If you want to specify, turn that into a question so I can answer, because I'm not just going to go on a whole explanation about black holes, because that would take me quite a while, or matrix theory. So if you have a specific question, let's go to that. Question from David Howden. As our brains presumably didn't evolve to do cosmology, I'm always surprised how much we can learn. Me too. Do you think we will ever get to the point where understanding is beyond human capacity? Oh, this is a nice philosophical question here, and I don't think so. Now, humans have always been curious about the cosmos. The tools we've used, the way we ask the questions, the way we do our experiments has changed. But humans have always looked up at the night sky and said, what's that? And we've always hypothesized about things. You know, we have civilizations that would look at the night sky and say, okay, you know, we're riding on the back of a turtle, or this is a Milky Way because someone spilt their milk in the sky. It might not be the theories that we accept today, but these people were already doing cosmology. You know, they were already looking at the night sky and trying to understand it. So cosmology and like the study of the cosmos and what's going on up there is something that humanity has always done. It's something that has always intrigued us. It's in many ways one of the oldest scientific disciplines we have. And I know some people disagree with this statement, like cosmology only started when we started applying the scientific method. That's nonsense. Scientific method is what we use today. And that doesn't mean that all previous science was wrong. You know, everyone has done science in different ways. And I think that this curiosity of looking at the night sky and saying, let's try to figure out what's going on up there, even if you reach the wrong answer. You know, in 100 years, people are going to be saying that what I believe today is nonsense. So even if you reach the wrong answer, just this idea of trying to understand the universe around us is cosmology. And this is why cosmology is one of the oldest disciplines. And this was a whole tangent and not really what you asked there, David. So will we ever get to the point where understanding is beyond human capacity? I don't think so. I also don't think we'll ever get to the stage where we've understood everything, where we've said everything that humans can understand about the universe, we've understood. I think the day that happens would be a very sad day. The day we say there is nothing left to learn, there is nothing left to understand. That's a sad day. I don't want to be at that point. There is always stuff to learn, there's always stuff to understand. Will we ever reach the point where we've understood everything? Absolutely not. You know, the more things we understand, the more we realize we don't know. It's like we figure out that 25% of the universe is dark matter, we still have no idea what dark matter is. We figure out the expansion rate of the universe, and now we might be wrong and the universe is expanding differently. We've measured this amazing map of the CMB and extracted percent level precision from it, and suddenly there's a new experiment that is showing that maybe this one is wrong. It's not wrong. Planck is not wrong. Planck is never wrong. It's like tiny, tiny, tiny discrepancies. Planck is not wrong. So, no, I don't think that we'll ever get to the point where understanding is beyond human capacity. We might reach a limit where we say, given our current technology, we've done the best we can, but then we'll just invent new technology because this is what humans do. And it's like, oh, we can't study the universe with our current tools, let's make new ones. So I am optimistic that the universe will never cease to understand us, never cease to amaze us, and will always remain just elusive enough that we can get some details, but not enough. That's what makes it fun to study, right? Knowing that everything I think today might be proven wrong tomorrow. But in the meantime, I'm just helping us along this journey of updating our knowledge about the universe. Dark matter is a turtle's eggs. I mean, honestly, dark matter is space dragons, dark matter is space turtles. Until we rule it out, it is a valid hypothesis. Space dragons is my default. Anytime I want like a crazy example of a dark matter theory or dark matter model, I throw out space dragons. And you know, if we ever actually find that dark matter space dragons, I will be so amused. We're not going to, but it's a fun thing to think about. Okay, back to the other questions. Let's see. Some great questions so far. I love these questions, of like these philosophical ones of the understanding of the universe and stuff. Would gravity exist without mass? So would gravity exist in a massless universe? Question by James. And this is also a really, really, really cool question. Having a slightly annoying cough today. But yes, this is a really cool question. So would gravity exist without mass? Space dragons are cool. I agree. Space dragons are cool. Turtles all the way down, including dark matter. Yes, it's just turtles all the way down. So the thing about gravity is that we don't know how it works much. We think it's a force we've understood. We think it's a force. You know, I drop a pen, it falls down. We're held in orbit around the sun. This is gravity. We understand gravity. But what is gravity? In Einstein's general relativity, gravity is nothing more than the curvature of space-time. Any object with mass is going to bend space-time. This curvature of space-time tells objects how to move. In this scenario, without anything bending space-time, without mass, you can't have gravity. Even in Newtonian's gravity, which is, you know, Einstein's general relativity reduces to Newtonian gravity in the extreme limits. And even there, if you calculate the gravitational force between two objects, it's always proportional to the mass of the two objects. So if the mass is zero, the gravitational force is zero. So if you think of gravity purely as a force, you need mass. If you think of it as the curvature of space-time, you need something curving space-time. Of course, then you can ask the fun question of, let's imagine the universe is curved. Currently, all of our knowledge points towards the universe being flat. But if the universe is curved, then you already have this curvature of space-time. Is that the same as gravity? No, it's not how we normally define gravity. But see, defining gravity becomes very difficult. Then there's a question of how does gravity act at the quantum level? And for that, we need quantum gravity, and I'm not quite there yet. No, none of us are quite there yet. So in that case, you know, all of the other forces that we know of have a particle that carries them. The electromagnetic force is carried by the photon. The strong force is carried by the gluon. It glues things together. We're so good at naming things. And the weak force is carried by the W and Z bosons. These are the ones that, anytime there is an interaction, these particles are being exchanged. So what about gravity? Well, gravity might be carried by the graviton, which is a hypothetical particle that would just carry gravity around, but we've never found gravitons yet. In order to understand gravitons, we need quantum gravity, which is uniting the gravitational world with the quantum world, and we don't know how to do that. So, would gravity exist in a massless world? Probably in a massless universe. Based on our understanding of gravity, no. Based on the fact that if we define it as a force, we need the masses involved. If we define it as the curvature of space-time, we need some object curving space-time. So based on that, no. But would it still be a force that particles could exchange? Would there still be particles like traveling between other particles in a gravitational interaction? It's unclear. So I'm going to answer that with a probably not, but with an asterisk saying happy to be proved wrong if we find more stuff about gravity. But it's fun because anytime we explain the four forces in the universe, we talk about gravity, you know, pens fall down, objects stay in orbit around each other, objects move through space-time. We kind of know what we're saying. For the electromagnetic force, you know, electricity, magnetism, we're all familiar with these. We see a light turn on, we see a magnet stick to the fridge. Strong force, we say, okay, it's what glues everything together. The strong force holds protons and neutrons together in a nucleus. It holds the quarks together. And then we say weak force, and everyone explaining the weak force is like, yeah, radioactive decay. That's it. Because the weak force is very difficult to explain. And then you say to people, there's one of these four forces that we don't understand. And everyone's like, it's the weak force. You know, you just mumbled something about radioactive decay. That's the one you don't understand. It's like, no, it's actually gravity. There's an XKCD about that. Just felt like I should throw that out there because it's fun. So let's see, more questions. These are all great questions. I appreciate that you all have really fun questions, especially today because I didn't prepare a topic. So now it's great that you all have questions. So we covered the CMB, we covered if there's a point where humans would stop understanding things. What gravity exists without mass, we've covered that one. Cutting an X out of a photo, we covered that. How often is the CMB updated? Did that one. Planck ended its data run? Yes, absolutely, in 2018. Let's see. Okay, on to Keith. Are there ways to hypothetically program only a patch of the universe and still have it exist symbiotically within the rest of the universe? I'm not really sure what you mean here by simulate a patch of the universe. Now, to the best of our knowledge, the universe is homogeneous and isotropic. This means it looks the same in any direction from wherever you look. There's no preferred observer. From this, we can do measurements in our close by neighborhood and extrapolate them to the observable universe, which is the patch that we have access to. So in a sense, anytime we do a simulation of how particles move, we don't simulate the whole universe, we simulate a small patch and then say this small patch is a valid representation of what's happening elsewhere, because why would this specific patch that I've simulated be special? Now, can you separate the wave function of the patch? I'm really not sure what you mean here, because when we're talking about big things like the universe, we don't really talk about a wave function of the universe, because wave functions is what we use to define the subatomic world, to define particles. A photon has a wave function, an electron has a wave function, a quantum system has a wave function. The wave function is basically all of the information of the system expressed in wave format. But when you move up to big objects, this quantum mechanics formalism breaks down. So the wave function of a patch of the universe doesn't really make sense, because when we're dealing with macroscopic objects, big objects, we have gravity at play, and we no longer use a wave description. But to the best of our knowledge, this patch of the night sky is the same as this patch, and this patch of the universe is not in any way different to this other patch. So if you can simulate one patch, you can extrapolate that and say this is a good representation of the universe as a whole. I'm not sure if that answers your question, but I hope that makes sense. I did not just mean to put that on screen. I accidentally clicked there. But let me just go back and see. There were, just want to see if there are replies to what I'm just saying here. Okay, we have another thing about gravity here. Let's see. Okay, let's carry on going through the questions here, because I think I'm close to catching up with the questions now, and there are some good ones coming in at the bottom. We did the wave patch, we did the turtles, dark matter's the turtle eggs. Okay, that's good. Question from James here. Does gravity span the whole universe, or is its power limited? If the whole universe consisted of only two baseballs on opposite ends of the universe, would they eventually come together? Excellent, excellent question here, James. And I like that you put ends of the universe in quotation marks. Now, the cool thing about gravity is it's the weakest force we know of. It is extremely weak. Now, What I mean by extremely weak is if you increase the distance between two objects by a factor 10, you decrease the gravitational force by a factor 100. So it goes like inverse to the distance squared. So when the distance multiplies by 10, the gravitational force divides by 100, which means the further away objects are from each other, the less they impact each other. Now, there will always be a gravitational force between these, but at some point it becomes so ridiculously insignificant that we don't need to worry about it. Like it would be so insignificant that it would never really have a realistic effect. This means that at some point, if you have two baseballs on opposite ends of the universe, or very, very far apart, they would not eventually come together. Also, then you have to factor in that the gravitational force, to the best of our knowledge, travels at the speed of light, which means if objects are so far away that light, the information of the gravitational force needs to travel from them, it's going to take quite a while for the baseballs to feel each other's effects. But the fact that the gravitational force is so weak is really good, because else everything already would have collapsed. There are a lot of supermassive black holes in the universe. In fact, there is a supermassive black hole at the center of the Milky Way. But it's not going to suck us in anytime soon because we are so far away from it. This is also the thing that a lot of people think black holes are these scary objects in the universe that are going to absorb everything. But because they're dominated by gravity, they are very, very not very long-lived in terms of distance, which means, yeah, there's a black hole up there, I don't need to care about it. You can also do the fun thing, like if you substitute the sun for a black hole of exactly the same mass of the sun, what would happen? And the answer is nothing. You can put a black hole in the middle. All life on Earth would be extinct because we'd no longer have our heat source, but the planet Earth would still continue orbiting around this black hole because it wouldn't be close enough to fall in. If it were close enough to fall in, it would already be falling into the sun. So gravity is very, very weak. So the further you are away from an object, the less you need to worry about the gravitational force. And then at that point, two things far enough away in the universe, you don't need to care about them. So it does kind of span the whole universe, but it is very limited in how strongly it can move objects. If you increase the distance by a factor 10, you reduce the gravitational force by a factor 100. Okay, we'd freeze to death, yeah. If we did put this black hole there, we would freeze to death. That is very true. But in terms of the Earth's orbit, nothing would change. You always think of the inverse square law being because gravity is being spread out over the surface of the sphere with the radius at distance. Yes, this is absolutely correct, David. I didn't even finish reading it, but I know it. Yes, this is absolutely correct. If you consider the gravitational force is moving away from an object, kind of in a spherical direction, in every direction, and it spreads out as it moves away. So it's not so much that it dilutes, but it is very similar to the way light travels from an object. Light also has this inverse radius thing. So it is also the way it kind of dissipates. Now, gravitational force doesn't really dissipate through the sphere, but it does get weaker as it expands into the sphere. That is a good way of thinking about it. Of course, the surface of a sphere, because else you have radius cubed. Okay, back to where I was with the questions. If the universe is curved into a sphere, we can see the back of our heads if we look far enough into distance. Yes and no. So when we talk about the universe being flat or curved, we have to remember that we're talking about a really, really, really big thing. Now, if the universe is curved, this does mean that light could hypothetically travel all the way around the surface. So if you shine a light and wait long enough, this light will travel all the way around the curved surface of the black hole and back to you. Now, the thing is, we are limited by the speed of light and we are limited by the size of the universe. Now, the observable universe has a radius that is 96 billion light years. So from here, if you wanted to get to the edge of the observable universe, which is basically where the CMB is, then you'd have to, where the last scattering surface is, which is where the photons that make up the CMB came from. The CMB is everywhere. So that's the diameter is 96 billion light years. The radius is half of that, so 43 billion light years. So that's already very, very long distance. So if then you add curvature into it, yeah, eventually light would come back, but it would take such a long time that we would no longer be around to see it. But hypothetically, yes. Now the thing is, from all of our observations, it seems like the universe is very, 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 very close to being flat, if not completely flat. So if it has any curvature, it's such a small curvature that it would take billions and billions and billions of years for any type of light to travel around. So hypothetically, yes, if the universe is curved, light would travel around it, but it would take such an infinitely long time that it wouldn't really matter on timescales of any species or any star for that matter. Gravity falls off as inverse square, yeah. So it's an infinite theory. I'm not sure this question is clear, but strong force only acts at a short distance. Is that because it just declines really quickly with distance, or does it literally drop to zero at some point? Ooh, wow, this is a very difficult question to answer, David. So the strong force is something that I should know how to explain, but the strong force is basically contained. Now, the strong force, normally when you find quarks, which are what make up all of the protons and neutrons and all of the particles, you don't actually find them free. You kind of have this quark gluon soup, and the strong force is actually ridiculously strong, to the point that if you try to rip two quarks apart, the energy you need to rip them apart produces more quarks, which is why you can never find one free quark. You can never go like, hey, I have a quark. Quark always quarks. No, quarks, if you have that variant. Always, quarks. It's a debate in the field. Everyone pronounces it however you want. As long as people understand each other, it doesn't matter how you pronounce things. But you always find quarks in pairs, in threes, in fours, in fives, in six groups. But you never find quarks alone. And the reason is they have such a strong binding energy with the strong force that just trying to separate them produces more quarks. So if you have a quark, like two quarks together, and you try to pull them apart, you're just going to end up with two quark pairs. It's the same as magnets. If you try to pull apart a north and a south, you just end up with a north and a south again. So the strong force does only act on a short distance, but it is a very strong force. The reason it acts on a short distance is something we're going to throw around as like confinement energy, which will take me a lot more energy than I have today to explain. So that's a great question, and it's one that I should know the answer to, but it's one that I'm just going to leave as like, let's come back to that someday. I'm going to make a note to review strong force. Now, there's always one that's like, yeah, it holds stuff together. It's very, very strong. But yes, it's a difficult one to explain. That is an excellent question. David, I was not prepared for that question today. Baseballs is an interesting question because maybe the expansion of the universe between those two balls would overwhelm the gravity. Yes, that is a great point to make there, Paul. As I was saying, if you have objects that are very, very far away, you also need to account for the fact that gravity travels at a finite speed, which is the speed of light. So it takes quite a while for the gravitational force to reach different objects. Now, if you add in that the universe is expanding, it might be that these objects are expanding so much, so far away from each other, that their relative gravitational forces will never reach each other because they're limited by the speed of light. So excellent point to make there, Paul. A broken cup probably won't spontaneously reassemble. Exactly. I'm not sure what this was a reference to, but yes, a broken cup probably won't spontaneously reassemble because of the arrow of time and entropy. And I know I've used that example a bunch of times anytime I'm talking about the arrow of time or entropy. So if I have 1,000 pieces of a broken mug, there's only one way you can put them together to make a mug, but there's thousands of ways you can break that mug. Going from a mug to a broken mug is easy because you're increasing the entropy, you're increasing the chaos and the disorder, and the universe likes doing that. It's energetically favorable, it's energetically efficient. If I drop my mug, it will break. If I find a broken mug, it's not going to spontaneously reassemble because that would require a lot of added energy, and it's not a process that the universe is going to do. Incidentally, that is also the reason why your headphones get tangled up. It's something everyone's experienced. You take off your headphones, you put them down, or Christmas lights, you take them off the tree, you put them down, you pick them up again, and they're tied up. And the reason is because there are thousands and thousands and thousands of different ways you can tie them up. And there's not many ways it stays organized. So to keep it organized, that's its default state. But as soon as anything acts on it, it can get altered. You take it out of your pocket, you put it in the box, you pack it away for a year, you come back to it, it's going to be tangled up because there are thousands of ways it can be tangled, not many where it can be untangled. And therefore, the universe tends to maximum chaos. Likewise, if your room is messy, there's 1,000 different ways your room can be messy and not many ways it can be tidy. And I used this as an excuse when I was a kid. Surprisingly, now I'm actually pretty much a clean freak and my place is always organized. But as a kid, it's like my room is messy, blame the entropy of the universe. So I'm not sure what your comment of the broken cup was a reference to. I think I might have said something related to arrows of time or entropy, but it's always a fun thing to talk about. Let's see, we talked about that. We'd freeze to death if the sun was replaced with a black hole. Yep. Orbiting a black hole, fun to think about. We would all freeze, but the Earth will carry on in orbit. Okay, so I see, let me just go back to a few more things at the bottom there. It's written quark, but it's pronounced warbler mangrove. Sure. I mean, it's like the dairy product, right? Quark, it's up to you how you pronounce it. It's also the thing with the LISA spacecraft that some people say LISA and some people say Lisa. And it seems like whichever person I'm talking to does the opposite of what I'm doing. And I just change every time. The last person I spoke to said Lisa, so now I'm saying Lisa. The next person said Lisa, so now I'm saying Lisa. As long as everyone understands what we mean, that's fine. I'm seriously befuddled that gravity has a speed. I'm thinking of gravity as a curve of time and space. That is a great point. And it's curious to think about gravity having a speed. One way to think about it here, I know there was a question I missed in between, I'm aware of that, I'll get to that in a sec. So one way to think about it is that things do not travel instantaneously throughout the universe. Because if things could travel instantaneously, they would kind of violate what we call causality. So something needs time to reach its effect. Things in the universe are not instantaneous. In the same way it takes, the light we see from the sun was released 8.5 minutes ago, it takes 8.5 minutes for the light to reach us. Anything that happens in the universe takes a while to take its effect. Now, one way to think about this is imagine you have the sheath of space-time, which is always this analogy we do, like a trampoline, and you suddenly put a planet there. So there was no planet before, now I'm just dropping a planet on you. Now this planet is going to curve space-time. And this curving of space-time is going to gradually affect things. It's not instantaneous that space-time is curved and everything suddenly is aware of it, because things don't travel instantaneously. What actually happens with the gravitational force is you make a planet spontaneously appear, you do the inverse Thanos click, so I snap my fingers and a planet forms. That would be a cool superpower, right? Instead of destroying things like, poof, I made a planet for you. So poof, I make a planet appear. This planet suddenly bends space-time, and this produces a series of gravitational waves which are going to travel outwards and carry this information. Gravitational waves may or may not be formed of a sea of gravitons, which are the particles that may or may not carry the gravitational force. That's less as a big question mark. But these gravitational waves are going to take a while to propagate through the fabric of space-time. Now, within Einstein's general relativity, within Einstein's theory of general relativity, gravity should travel at the speed of light. And saying the speed of light is kind of a misnomer. It's actually the maximum speed of information. Light travels at the maximum speed of information, so does gravity, in Einstein's general relativity. There are a lot of other alternatives to Einstein's GR, which are known collectively as modified gravity. And when you modify gravity, what you do is you take some of the assumptions that go into Einstein's general relativity and you change them slightly. There are different reasons to do this. Some theories of modified gravity seek to explain why we have dark energy. Some seek to explain dark matter. Some just try to ask a question of, is there something we're missing with Einstein's general relativity? But a lot of models of modified gravity predict that gravity travels at a different speed. That is not the speed of light. However, a couple of years ago, we got the first ever Joule measurement. So we got a measurement of two neutron stars smashing together. Now, these two neutron stars smashing together produced a huge amount of gravitational waves that LIGO, the ground-based gravitational wave detector we have was able to detect. And at the same time, these two neutron stars smashing together produced a huge burst of electromagnetic radiation, gamma rays, which then were redshifted, and you got across all the whole range of the electromagnetic spectrum. And by measuring how long it took the gamma rays to reach us versus how long it took the gravitational waves to reach us, these measurements arrived within 2 seconds of each other. And if you consider this was 200 million light years away, an uncertainty of 2 seconds is ridiculously low. This measurement showing, you have the neutron stars crashing together, the light traveled out, the gravitational waves traveled out, they raced towards us, and they reached us basically the same time. With this measurement, we were able to say gravity travels at the speed of light to within 99.999999, a bunch of 9% accuracy. So just it's very, very difficult if this measurement is true, which we have no reason to doubt it. It was verified by a bunch of different collaborations. Then gravity travels at the speed of light. This is really cool because a lot of modified gravity models stopped working immediately. They were falsified with one measurement. There's a lot that still work, and there's ways you can change them to salvage this. But personally, it was very amusing because the day they announced that measurement, the next day I was attending a talk on modified gravity. And the guy started his seminar with, well, the measurement announced yesterday basically kills everything I'm talking about today, but let's do this seminar anyway. And he spent all of the seminar talking about these models. And it's like, anyway, now I'm going to show you how many survived after yesterday. And he had like 100 models on his screen, and suddenly 80% of them went away. It was just very funny timing that we had that seminar the day after the announcement. It amused me. Hey up, Trey, great to see you. Thank you for coming by. I think you're a new follower, new viewer here, so welcome. Great to have you here. Any questions about the universe, throw them at me. I'm going to try to answer unless you ask me about the strong force, and then I'm going to hand wave that one away. But feel free to ask anything you want. Okay, question from Keith a while ago. If you could perfectly simulate a distant reality in a level 1 multiverse, would you exist both here on Earth in the simulation as well as wherever that real reality exists? I'm really confused by that question. I'm not sure what you mean by simulating a distant reality. I'm not sure what you mean by level 1 multiverse here. So I think we're getting into very metaphysical questions. Anytime we talk about the multiverse, it's going to be very metaphysical. And just a reminder that quantum entanglement refers only to quantum world. Again, when we move to larger objects like people, like a whole universe, you cannot apply the laws of quantum mechanics. Quantum mechanics is only good, or is very, very good for small things. But above a certain size, like even when you're talking about molecules, this is too big to be described with quantum physics. So at this point, you need different physics, different maths to describe things. So quantum entanglement is really only for small things. I often use an example of like two bunnies in a box. One is evil, one is good. But this is just a thought experiment that we do, like a mind game, because quantum physics is really only to describe small things. So if you're talking about simulating universes, you can't really apply quantum physics to describe this universe you simulated. Okay, so let's see, entropy. Yes, entropy, always a good argument. People who can visualize radiation and gamma rays fascinate me. I thought I was the odd one out. So human eyes can only see a specific range of the electromagnetic frequency, which is the visible one. Some people have a slightly broader range. Dogs can see a different range. I think there's a specific type of jellyfish. Is it a jellyfish? Or no, there's a specific type of squid that can see in ultraviolet. I have no idea why a squid needs to see in ultraviolet, but a squid can see in ultraviolet. But most humans are limited to seeing a specific range of the electromagnetic frequency. This is where our eyes are designed to work. The thing is, if you had eyes that could see gamma rays, you wouldn't be able to simultaneously see anything else. So you can, if by visualize it, you mean kind of imagining how you would think about it, yes. But actually, your eyes cannot have any receptors for anything outside of a specific range in the electromagnetic frequency. So visible is what we are biologically, what we have biologically. We're not on the different ends. But it's curious to think about what some species with a radically different visual range would see. Then there's also the question of, it's highly convenient for us that our eyes have evolved to see the light that is the best one we have coming from our sun. So it makes you wonder, if we were on a planet around a very different type of star, would our eyes have evolved to see the same range? So that is a very interesting question that a lot of sci-fi authors have exploited. So thank you for your questions, Keith. I do appreciate trying to answer them. They are very complicated questions, so I hope I can give you somewhat believable answers. Yeah, some guy memorized pi to 22,000 places. The world is indeed more bizarre than we think. Exactly. Everyone has different talents. Some people can memorize things 22,000 digits. I could not. Some people have great visual spatial recognition. Everyone has different talents, and it's true that humans are incredible and diverse, and we'll never understand the diversity. And scientists are often like, every human does this, and then we find a human that doesn't, and we're like, I guess not. So yeah, every human is unique. Every human has random, weird talents that will make us special. Or weird, but also good. So yeah, universe is crazy. Humans are weird. All surgeries to replace parts of the eye apparently did let some UV light in to be seen. Ooh, that's cool. That is very cool to think about, that some people could see different ranges of the electromagnetic spectrum. And then we get into a very fun question of, when I see something and say this is red, am I seeing it the same color that you are seeing it? Is my red the same as your blue? So yeah, because we identify like this color that I'm seeing corresponds to this wavelength. But then how do I know that the receptors in my eyes are processing the wavelength in the same way you are? What if every time I say like the trees are green and everyone's like, yes, green. But if we change receptors, like if I had your eye receptors, would I then say, actually, these trees look kind of red to me? Of course, then you can throw in color blindness and everything gets really fun. But it's really curious to think about if when I say red and someone else says red, do we mean the same thing? But then you could do that with everything. Like when I taste something sweet, how do I know that sweet for me is the same as sweet for everyone? And then we get really metaphysical, which is great fun if you have a couple of glasses of wine, but definitely off topic and off on a tangent. Thank you for your nice comments, Keith. And yeah, you can interact. That is the purpose of Cup of Cosmology. So I feel like there's often the perception that scientists are these crazy, unapproachable geniuses. This is fundamentally wrong. Scientists are people like everyone else. We make mistakes. It's stuff we don't know. A lot of us have issues. A lot of us are arrogant. Not everyone. Scientists also come in every possible personality type. And I don't think science should be seen as unapproachable because the research I do is funded by public money. Science has always been something that belongs to all of humanity, and it's something that everyone should be able to participate in. And I'm very lucky and very privileged that I get to study science for a living. This is something that I am extremely grateful for and I find extremely fascinating and extremely fun. But what is the point of understanding stuff about the universe if I can't share that with people? And what is the point of doing it? To hoard knowledge for yourself, like a dragon sat on your hoard of knowledge? Back to space dragons again. So yeah, I love interacting and answering these questions because this is the purpose of this show. This is why I'm here, to answer your questions. Sometimes I won't know the answers. Sometimes your questions will baffle me, and I'll have to figure out how on earth I answer that. And that's just part of it being fun. So I appreciate all of you coming here. I appreciate all of you asking these questions because I love trying my best to answer them and trying to prove that science is not this weird, mysterious, unknowable thing. Science is amazing, and it's an endeavor of all of humanity. And we all belong here in science, and we all deserve to get these questions answered. I just got very, very deep there for a moment. So we need another hour of cup of metaphysical cosmology. Someday. I do actually have like 3/4 of a bottle of wine in my fridge, and I'm not an alcohol person. So we could do a drunk cup of cosmology one day. I fear that would just turn into a lot of rants about stuff, even more than usual. But yeah, we could do metaphysics someday. It's always fun topics to go down, but that should come with a big disclaimer, like everything we say here is up to interpretation, which, to be fair, you should always take anything I say with a pinch of salt, with a grain of salt, because yeah. Random moth fact. Oh, I love random moth facts. People with red-green color blindness can easily see emperor moth caterpillars, which are very camouflaged to those with normal vision. That is incredibly cool. That seems like a superpower, actually. It's like, okay, you mix up red and green, but you can see this random bug that nobody else can see. That's a really cool fact, David Hogan. Thanks for sharing that with us. That's really cool. Thank you for all of the lovely comments. Never trust a non-drinker. Yeah, well, each to their own, right? Each to their own drug of choice. I have tea, I have coffee. I am slightly caffeinated today, which is potentially why I'm hyper. I had the dinner party yesterday. It was great fun, and I made a big pot of coffee just in case anybody wanted coffee, and nobody wanted coffee. And I may have drank a bit too much of the coffee today, which is why I might appear to be slightly hyper. Drunk cup of cosmology would be great. We need a pre-show to drink a few cups first. So we can all start. Drinking game, take a shot anytime Diana mentions the CMB. Okay, this is a very bad idea. But you could set up a drinking game around my show, and I'll join in, and then we immediately go into drunk cup of cosmology. I should get guests for that, because if I do it alone, it would be weird. But yeah, we should do that someday. I think there was actually a podcast called Drunk Scientists, and it's just people having a laugh and then talking about their science, slightly tipsy, and it gets very fun very fast. But yeah, maybe someday. And thank you all for the nice comments. It's great to see so many of you coming here and asking questions. Today I didn't have a topic prepared. You all asked such good fun questions that we were able to make it to the hour mark without me having to go off and ramble about stuff. Well, I did a lot of rambling, but they were questions that guided us through the conversation. So thank you, everyone, for asking your questions, for coming here, for chatting with me, for making me think about the strong force again and everything we've covered today. It's always great fun to come here on Cover Cosmology. I should have a guest on soon, not yet sure when. Going to plan a guest, and one just put out a paper recently, might want to be on the show for that. Going to plan that. Got a few things planned, but nothing concrete. Is it true that the JW proved there was no Big Bang? No. Short answer, no. JWST telescope has not proved that the Big Bang was wrong. That's a couple of headlines blown out of proportion. We can cover that next week. Not going to go into it now because I am wrapping up, but short answer is no. But we can cover that at some point. So I will be online again next Sunday, same time as today. That's 7 p.m. Central European Summer Time. 1 p.m. if you're on the East Coast. 1 p.m. if you're on the East Coast, 10 a.m. if you're on the West Coast of the US. There is a time zone converter on cupofcosmology.com, so you can put everything in your own time zone. If you want to watch more episodes of Cup of Cosmology, if you can't wait till next Sunday, check out the playlists. There is one playlist of the best of Cup of Cosmology, and there is another playlist I made today. So do check out the playlist. If you haven't subscribed, do so. Leave a comment, like the video, all of the usual YouTube stuff to increase visibility. Tell your friends about the show. If you know any good scientists who want to be a guest on the show, let me know. We can try to set it up. Thank you, everyone, for joining. This has been really, really fun. I hope to see you all again next Sunday, and I hope in the meantime,